Hey everybody, it's Ripley again. We're going to do another really easy section out of Chapter 6. Chapter 6 is crazy because like half of it is really hard and the other half is just like, wow, this is the easiest thing I've ever done. By the time you're done with this video, hopefully you'll have an understanding of what the average value of a function is. We'll also throw an example in there for you. All right, so think about this. What I want to do is, let's say we take the function y equals x squared and we go from, I don't know, from 0 to 3. Okay, and what I want to do is I don't want to figure out the area under the curve. I don't want to figure out the length of the curve. I want to figure out the average value of the curve. In other words, what is its average value? If it was theoretically possible to add up all of the values, remember there's an uncountably infinite number of values of y equals x squared between 0 and 3. But if there were only a way that I could add them all up, boy, wouldn't my life be so good. All right, so he says glibly with a smirk on his face. All right, let's think about how to find an average. Just in general, if I'm trying to find an average of an average age in a class, how do I do it? Well, I add up everybody's ages, right? So I take some data point, D1 plus D2 plus D3 plus dot, 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 plus D sub n, and then I divide by n, right? Nothing to it. Easy. So what I'm going to do, if I can apply that to the function, couldn't I just as easily go y1 plus y2 plus y3 plus dot, 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 plus yn. Now this assumes that I have these discrete values, right, that I can just pull out one at a time, order them, and then divide by n. Now we know that that's not true, but we actually have a way around this. Now think about this. The average value is equal to f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus dot, 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 plus f of x sub n, right? Now, that assumes that there is a fixed number n of values on this. The problem is we know that that's not a fixed value, but think about what we're really doing here. Let me change color. What I'm doing is I take a value right here, and this is going to be I'm just going to kind of arbitrarily choose a value, a slice of action, if you will, and I'm going to call that x sub 1. And then I slice off another little chunk, and I use as a reference point x sub 2 to get the f of x, right? And then I slice off another little chunk, and I use that as a value. I'm running out of room here. Let's call that x sub 3, etc., all the way up until I get up here to x sub n, right? Oh, by the way, this should be divided by n. Sorry about that. All right? So, divided by n, right? Now, theoretically, can you think about this? If I could take these little slices of these little individual points and I could shrink their width down to 0 so that I'm counting up an infinite number of infinitely thin such data points, wouldn't that work? You smell that? I smell an integral in the air. But we're going to have to do a little bit of work here. Just now, let's think about this for a sec. How am I going to, because remember what an integral has. An integral has an integrand, some f of x thing, right? And then it's got a dx. And then it's got limits, right? Now this is the basic structure of every definite integral. So I'm going to have to manufacture this dx here somehow. If only there were a way to, wait, there's an n right there. Wait. Remember when we first started playing around with integrals? Didn't one of the components of our integrals have an n in it? Do you remember what that was? Oh yeah, it was delta x. Delta x was b minus a divided by n. So doesn't that imply algebraically that n is equal to b minus a divided by delta x, right? You agree? So in other words, I can rewrite this as f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus dot, 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 plus f of x sub n divided by b minus a divided by delta x. So think of b minus a divided by delta x as being its own fraction. So this guy ends up being f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus dot, 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 plus f of x sub n. The whole thing, remember when I divide by fractions, I invert and multiply, or I reciprocate and multiply, divided by b minus a. Right? That's what the average value is. Now, what is the mechanism by which we add up an infinite number of infinitely thin things. What's the integral? That's the integral. We could almost think of this as being the average for some, I don't know, what could we say, for some fixed n. I guess it would be an average of n. That would be one way of saying it. However, we now have this tool, this wonderful tool called the definite integral. So don't I know that the exact average value, that's supposed to be an e, is equal to, you ready? It's the sum of all of the values of f of x, which is simply the integral from a to b of f of x. What do delta x's turn into? Well, the thickness of these little guys over here goes arbitrarily close to 0, so delta x's turn into dx, and then we have this little extra guy along for the ride. Isn't that awesome? Just another really clever, really elegant way to use integrals. Now, let's actually do this for x squared, just for giggles. All right, I want to know average value of x squared on the interval, from 0 to 3. Well, check it out. It's simple, right? I'm just going to go the integral from 0 to 3 of x squared dx. And then sometimes you'll see this written like this, 1 over b minus a times the integral from a to b of f of x dx, right? So this is just going to be 1 over 3 minus 0. So this is 1/3 times x cubed thirds from 0 to 3, right? So plug a 3 in, I get 27, divide by 9, I get 3. Well, that's kind of cool. If you think about that, it says that the average value of x squared from 0 to 3 is actually 3. Now, I know that this point, let's see if we can put some sense to this. I know that this point is 3 comma 9, right? But if you think about how x squared behaves, it spends a whole lot of time, particularly between 0 and 1, way down here. In between 0 and 1, like you take a number between 0 and 1 and you square it, you get an even smaller number. So it spends a bunch of time being really close to 0 before it really lets itself take off. And that's why we end up with the average value that we get. Now that may be counterintuitive. You may say, wait a sec, but it really popped up here to 3,9. I mean, it raced up to 9. Yeah, but between 0 and 1, it was really close to 0 because numbers less than 1 squared are even smaller. So that's kind of a cool application of the average value. All right? All right. Now let me show you one of the really cool ramifications of the average value of a function. All right, and I'm gonna need a little space here because I'm gonna draw kind of big. What we're going to end up with is something called the mean value theorem. Remember the mean value theorem for derivatives? That given f is a differentiable function, that we know the average rate of change of the function equals the instantaneous rate of the function. Remember that guy? For at least one value between a and b on a closed interval. So the mean value theorem for integrals looks like this. For integrals. Okay, so excuse me. All that it says is we already know that the average. Oh wait, let's give you suppose f is a continuous function on a closed interval from a to b. Boy, that's starting to smell pretty familiar, isn't it? Right? All of our value theorems start with suppose f is continuous. Otherwise, we're dead. Although mean value theorem for derivatives said that f is differentiable, which implies continuity. Okay, so we know that the average value of f is equal to 1 over b minus a times the integral from a to b of f of x dx. Now you may be looking at this going, wait, Ripley, why are you showing this to me again? I already saw it. Well, let's look at it graphically for just a sec, because this is pretty cool. Let's say that we have a function that does, I don't know, just something fun like this from, let's call that a, and let's call this b. Now you can look at this thing and say, oh, I don't know, where do you think the average value is? Let's just eyeball it. Okay, let's just eyeball it and call this the average f. All right. Now, I'm going to show you something. It's such a simple algebraic tool. All right, it's just one little move. And what this says is, if I cross multiply by b minus a, then the average value of f. Now I'm going to put this thing in brackets. Your book Your text uses this thing that looks like this, but I don't know. We got too many F's floating around, and this is this weird script F, and forget about it. All right? Your average value of F times b minus a is equal to the integral from a to b of f of x dx. Now let's think about what that really means. And this is wonderful because I got all these fun colors to do it with. The integral from a to b, this is for any continuous function on a closed interval from a to b. The integral from a to b is all of the area under that curve, right? You agree? Nothing to it? Now, what is this? What is the average value of f times b minus a? Well, the average value of f is a y value, and b minus a is an x value. But you guys know me, I'm simple country folk. That smells like a height and a width of a rectangle. This is the area of a rectangle, which implies, if you think about it long and hard, if I build the rectangle that is average value of f high and b minus a wide, that this area and this area, and this area are equal. A1 equals A2. Now, this may not seem too earth-shattering to you, but if you really think about it, it's pretty cool. It says no matter how goofy my function looks, as long as it's continuous on a closed interval, there is a rectangle whose area is exactly equal to the value of the integral. Now, again, that may not seem terribly earth-shattering to you, but it's pretty cool. It's really cool. It's a cool ramification, and it pops up from time to time. And I wanted to show you some applications for integrals. So hope you enjoyed it. We'll play with these tomorrow in class. Thanks for listening, and have a great day. Bye-bye.